Welcome to Practice number 95, and today we're talking about experiments on swept blades on wind turbines. So we're looking at the power output and the wake flow characteristics. And this comes from the other podcast that we did, number 94, where we looked at some numerical simulations and how to numerically simulate a wind turbine. So we covered a bunch of different principles. And we're going to be covering this paper again, output power and wake flow characteristics of a wind turbine with swept blades. And this is open access. So let's go on to the experimental side because we did the numerical side last podcast. Just a brief recap on that. They found that they were looking at sweep on going backwards and sweep going forwards. And they found that the turbine blades with swept forward blades produced about 2.5% more power and thrust than the straight blades. And the swept backwards blades, they were a little bit better, but not much. It was marginal. And considering that these were found in numerical simulations, the amount that they found for these swept back blades were probably going to fall inside the error of these simulations because they were only like 0.3% or something. Whereas the other simulations, the other swept forward blades, they had like a 2.5% increase. So they were probably realistic of the real life situation. So let's continue with the experimental setup. And you can find this paper in the link in the description. It's open access. So they say, as mentioned above, swept blades can make a difference to the wind turbine's output power and wake characteristics. So they have a picture here, figure 7, showing the setup of their wind turbines in their wind tunnel. They say the wind tunnel had two sections in their particular wind tunnel, a high speed and a low speed section. The size of the former, so the high speed section, was 3 meters in length, 1.5 meters in width, and 3 meters in height. And the maximum wind speed was 50 meters per second. The size of the latter, so the low speed wind tunnel section, had a length of 3 meters, a width of 3 meters, and a height of 7 meters. So that's massive. And the maximum wind speed was 25 meters per second. So that's still very high. And the turbulence intensity of both of these sections were less than 0.5%. So this is a very nice wind tunnel. And the reason why we have two different types, two different sections here, often we have different sections in a wind tunnel to have different conditions, flow conditions. So for example, if you want to have a atmospheric boundary layer wind tunnel, an atmospheric wind tunnel, for example, and another one where you want to have an aerodynamic wind tunnel. Or in this particular case, they have different cross sections. And the reason why you might want to have that is to be able to accommodate bigger objects and not have to worry about the blockage ratios. And I've done podcasts on the blockage ratios before and how oftentimes the blockage ratio is too large even for correction factors to make them useful, really. But let's continue here. So they say in experimental procedure, let's continue with this wind tunnel here. I've screwed out a little bit. So they say the model wind tunnel with the DTU LN221 airfoil had a rotor diameter of 400 millimeters, and the center of the rotor was located 400 millimeters above the wind tunnel floor. The whole wind turbine rotors were printed with 3D printing technology, and a 12-volt permanent magnet speed regulating direct current motor was used to achieve an RPM of 3,500. Due to the small scale of the turbine, the blockage ratio was only 1.4%, hence the blockage effects were negligible in this test. That's really good. Often blockage ratios are around 3%, 5% people would usually run at. So to get 1.4% is really nice. And that means that there's going to be almost no blockage effects or anything else like streamline curvature, for example. These are all parameters that can severely affect the performance of your setup and the validity of the setup. So in here, they have a very nice setup. So in the experimental procedure, they say, generally speaking, the power characteristics of the wind turbine was measured by a torque meter. The two ends of the torque meter were shaft connected with a hub and the motor with a controller, respectively. The rotation speed could be kept constant by adjusting the load, so the measured torque and rotation speed could obtain the output power of the wind turbine. So that's how they found that there. They say that a Hall sensor was installed behind the wind rotor to monitor its speed. So a Hall sensor just is a small sensor that can pick up magnetic fields, and they're very common. You can buy them for like $1. That's what they're using here. So then they go on to something which we never really cover, but is very important. They say the repeatability tests were carried out at different periods to verify the visibility of the test and accuracy of the data. So repeatability tests are often, if they're done, they're not really reported on. So it's very nice that they're doing that here. And they say in figure 8, they have them here. They have a bunch of tests, 5 of them, over different tip speed ratios. So the tip speed ratio, if you remember from last podcast and other podcasts on wind turbines that we've been doing, is the ratio of the tangential velocity of the tip of the blade compared to the free stream velocity. So if it's equal to 1, that means the tip of the blade is moving at the same speed as the free stream velocity. So in figure 8, they say that there's little difference in the average power coefficient curves drawn on the 5 repeated tests. So in other words, it's very repeatable, this setup. And you can see here that they land bang on each other. So that's very nice. They say the Pearson's correlation coefficient of any two tests were greater than 0. If any of the Pearson correlation coefficients of any two tests were greater than 0.929, then that meant that it was a good repeatability, which I found here. Meanwhile, comparing the test results with the CFD simulations results, the power coefficient values obtained by the two methods were close. The simulation results were slightly larger due to the mechanical loss in the test procedure. So now I'll come back to this in a second. Let's just continue a little bit with what they're saying. The simulation results were when the tip speed ratios were 2, 3, and 4, the relative errors between these were 7.42%, 6.19%, and 5.56% respectively, and the errors were constrained within 10%. The possible reasons for the slight difference between the numerical simulation and the tests were when the tip speed ratio was relatively low, the large area of flow separation could occur from the blade surface. For significant unsteady characteristic conditions, such a large separation and deep stall, the time average results may be delayed compared to the experimental results. So the RANS approach that they had in CFD couldn't predict the flow separation properly, they're saying here. Moreover, the rotor was made by 3D printing and directly connected with the motor shaft. The possible vibration in the test would cause a slight deformation of the blade, resulting in deviation of the aerodynamic force. So that's another potential reason why the CFD is different to the experiments in the results. However, there's a third reason here, which is the method that they selected to simulate the rotation of the blades. We covered this in podcast number 94. I'll just go through that briefly. So the method that they chose to simulate the rotation of the blades resulted in the blades not actually moving in the CFD. There was a sort of like an artificial movement where they kind of said, okay, we're going to apply a boundary condition here saying that the walls are moving, but they're not actually moving in the geometry. So what that means is if you have time, like let's say 1 second, and you have the blades at a certain position, well, at time 2 seconds, the blade's going to move differently, and the wake from one of the blades is going to impact the other blade coming behind it. But if you don't have the blades moving, you might still have that wake impacting the other blade, but not in the same way because the blade is at a different angle now to what it would have been. So that's one major limitation of the way that you simulate the rotation of the blades. There are ways around that. There are better CFD simulation methods, but they are far more expensive. So that is another reason why the CFD probably didn't align with the experimental results as much as they could have. So let's move on now. The wake field in the test was measured by a two-dimensional hot wire anemometer probe. This is from Dantec with an accuracy of 0.001 volts and a relative error less than 0.1%. So that's very nice. Dantec make good hot wire instruments, as do TFI. They're two major brands. So the test measuring points were distributed in the horizontal plane at hub heights 0.5 diameters, 1 diameter, 2 diameters, 3, 4, 3, 5, and 8 diameters behind the wind rotor. One measuring point was arranged at every 1 centimeter from the hub outwards. Considering that the radius of the wind rotor was 20 centimeters, the measuring range extended from the hub center to both sides to 30 centimeters. So that means that there were 61 measuring points in total along the horizontal axis effectively through the wake of the wind turbine. So this is effectively a one-dimensional wake survey. A two-dimensional wake survey is when you take a plane behind or in any other direction. If you want to understand what they are, just check out our CFD on our YouTube channel. We have a bunch of fun CFD simulations where we always do planes behind. And if you want to do a three-dimensional wake survey, it means that you have to do all 3 dimensions and get like a cube. Or it can be any other shape if you want to, but cubes are the most common. So besides stochastic uncertainties may occur in the measurements due to the discretization of the instantaneous velocity. So in other words, if you take a measurement at a certain point, if you have an unsteady phenomenon, then you're only going to be getting what's happening at that flow at that point in time. So you want to keep your probe there and take many measurements and then average them out to get an understanding of what generally was happening over time. and that gets rid of potential errors. So to do that, they had a large sampling rate. So they had 1 kilohertz and 5 kilohertz, and they took samples for 20 seconds. So that's very nice, and that's probably going to be more than enough for wind turbines, particularly of this scale, because the initiating frequency from anything around here is going to be significantly faster than 20 seconds. So you're going to get more than one cycle, and probably more like 10 or 20 cycles. So the average of that is going to be nice. So the results of the wind turbines with swept blades. The wind tunnel tests were conducted on the wind turbine models with straight blades and swept blades designated as F2010. And if you remember from podcast number 94, we were looking at swept forward blades and swept backwards blades. The F at the front of this designation indicates that they're swept forward, and the 2010 indicates how much they're swept. And we have two different sweep amounts effectively, and this is the moderate amount. Then there was the like extreme amount, and that didn't seem to perform as well as this moderate amount in the CFD. So they used this moderate swept forward amount, which produced about a 2.5% increase in the torque and power productions. And they say they selected 4 yaw conditions of 0 degrees, 10 degrees, 20 degrees, and 30 degrees to explore the power characteristics at different values of the tip speed ratio through wind tunnel experiments, and measured the wake of the wind turbines at the 0 degrees and 20 degree yaw angles to study the wake characteristics. So this is really nice because obviously wind turbines are susceptible to yawed oncoming flow, and they do change the power output and the wake characteristics of these wind turbines. So they're looking at 4 different wakes in terms of the power coefficient, but then they're looking at 2 different yaw configurations for the wake situation. And the reason why is because wake surveys do take significantly longer than just regular force measurements. So now let's move on to the analysis of power characteristics of these wind turbines. So in figure 11, this illustrates the power coefficient curves of the wind turbines with straight blades and swept blades in different yaw configurations. So just briefly, let's recap power coefficients. That is the amount of power that you're extracting compared to how much power there is to extract out of the flow. And again, we went through the mathematics in the last podcast, number 94. So they say at low tip speed ratios, both produced almost the same output power at the same yaw angle. As the tip speed ratio increased to a larger value, the power characteristics of the wind turbine with the swept blades F2010 were improved compared with the wind turbine with straight blades. And the output power increased, obviously, especially in the yaw condition. So that's interesting. Yaw actually is beneficial for swept blades. I wouldn't say beneficial, let's say, but it's swept blades are more immune to yawed conditions than straight blades. That's probably a much better way of saying it. At yaw angles of 10 degrees, 20, 30 degrees, the maximum power coefficients of the wind turbine with the swept blades F2010 were increased by 1.3%, 10.3%, 13.2%, and 16.7% respectively, in contrast to the straight blades. So in other words, as the flow gets more and more yawed, the swept blades perform better and better compared to the straight blades. When the power coefficients reached the maximum, the yaw moved the value of the forward swept blades, so they moved them higher. Besides, with the swept blades F2010, the wind turbine with the highest power coefficient had larger values than the one with straight blades. In different yaw configurations, the improved range of the wind turbine power of the swept blades differed from the straight blades. For example, the output power of the wind turbine with the swept blades F2010 began to increase at tip speed ratios of 4.5, 3.5, 2.5, 1.5, respectively, in the 4 yaw conditions, indicating that the larger the yaw angle is, the greater the improvement range of the wind turbine output power is. So in other words, as the yaw angle increased of the oncoming flow, the point at which the tip speed ratio at which the swept blades become better at compared to the straight blades became lower and lower. So in other words, at slower rotational speeds, the swept blades were still producing a better output power than the straight blades with increasing yaw angle. That's what this means here. They say the probable reason may be that in the case of the yaw conditions, the projected area of the rotor plane decreased in the inflow direction. So the energy flowing into the wind turbine will decrease. So let's look at the analysis of the wake velocity characteristics. They have a bunch of graphs here showing the hot wire measurements, showing the velocity deficit behind the wind turbine, so the wake in a just one line, a one-dimensional line. And we can see when the x on r position equals 0, this is when we're at the center of the hub, so center of the wind turbine. And then when it equals 1 or -1, it means we're at the edge of the wind turbine, so we're at the radius of the wind turbine. And they have on the y-axis the u divided by u naught, and u naught is the free stream velocity, and u is the wake velocity at that point that you are. So it just shows the normalized wake. So they say, figure 12 reveals the streamwise time average velocity distributions of the wake of the wind turbines with straight blades and swept blades when the tip speed ratio equals 4.67 without yaw. So the streamwise time average velocity distributions. That means streamwise is the free stream direction. The time average means that they're averaging this over a 20-second period each point to get rid of any potential stochastic errors. And it's the velocity that they're measuring. And the tip speed ratio is 4.6. The wake velocity was dimensionless. As we mentioned, they normalize it to the free stream velocity. It can be seen from the figures that, owing to the rotation effect of the turbine, the wake of the wind turbines with straight blades and swept blades presented the phenomenon of velocity deficit. So in other words, behind the turbine, there's significantly lower velocity. In fact, for a lot of these, you're getting down to only like 15% of the free stream velocity. So it extracts a lot of energy from the flow. So the streamwise time average velocity distributions at different sections of the wake's area are basically presented a symmetrical distribution along the center line of the rotor. As the wake continued to develop downstream, the velocity distribution gradually changed to a V shape. So in other words, behind the turbine, the closer you get to the hub, the greater the velocity deficit, and the further away you get from the hub, the less the deficit. So you get this V shape in the wake. At 0.5 diameters and 1 diameter downstream, the minimum wake velocities at the rotor center of the wind turbine with swept blades and straight blades were almost the same because of the intense development of tip vortices and central vortices in the near wake region. The radial distribution of velocities at the center height of the rotor fluctuated wildly, showing a W distribution. So in other words, these tip vortices that are occurring, and just vortices in general, they're manipulating the flow downstream, and instead of getting the regular V shape, you get actually a slight increase near the center of the rotor, and then its deficits behind it. So it's not a lot, but it is slightly more than what you'd expect. So it's not the typical V shape. That's what they mean here. Moreover, because of the tip acceleration effect, the velocities at the blade tip were higher. The velocity deficit in the central vortex region was prominent, and the minimum streamwise velocities only recovered to about 18.5% and 21.7% of the oncoming flow. As the position moved towards the blade tip, the wake progressively recovered. Additionally, it can be clearly seen from the figures that the wake recovery of the wind turbine with swept blades was slower than the one with straight blades. That's interesting. Now, they say, and the speed deficit of the wind turbine with swept blades at the same position was severe as well. As the wake of the wind turbine recovered at 2 diameters, 3 diameters, 5, and 8 diameters downstream, the minimum velocity at the rotor center of the wind turbine with the swept blades of the straight blades recovered to 29.8%, 51.1%, 59.0%, 68.7%, and then a bunch of other percents as well of the oncoming flow, respectively. That's not really important. The main things are that the further downstream you go, the more the wake does recover, and it gets up to like 70% of the free stream velocity to begin with. And the straight blades do recover quicker. They have, overall, they're about 4% higher the recovery percentage. So why is that? One possible reason, is that the swept blades were producing a lot more power, which means that they're extracting more energy out of the flow. So if you're extracting more energy, it means that the flow is going to be slower. So that's potentially why the wakes are not recovering nearly as quickly, and they won't recover as quick. They won't recover at all to the same extent as the straight blades, because you're taking out more energy potentially. So what that means is, for wind farms, that might pose a problem where if you have a lot of wind turbines around, they might be affected differently compared to straight turbine blades. However, if the swept wind turbine blades perform better, it means you might only need fewer of them to get the same amount of energy. So, moving on, The wake recovery of the wind turbine with swept blades was slightly slower than the straight blades. They're talking about this now. It is important to note that although the shape of the blades only changed near the tip position, the swept blades decreased the average wake velocities in the whole wake region. Such results indicated that the flow near the tip of the swept blade has an expansion effect along the spanwise direction. So this is interesting. This is the final thing they're talking about here, where even though the swept part of the blade is only on the outer part of the blade, the inboard part near the hub is also being affected as well. So obviously the flow physics near the outboard section is affecting the inboard section, and that's very common when you have all the flow in a flow field is connected somehow through pressure and viscosity, etc. So if you change one parameter, that's going to change other parameters around it as well. In this particular case, they said that the sweep outboard is affecting the flow physics still. So that's in this podcast in terms of the experimental results. What they found was that experimentally, it agrees with their numerical simulations in terms of the swept blades performing significantly better. But in the experiments, they found that the swept blades performed even better. So in the numerical results, they found it was about 2.5% increase. In these results, the swept blades were performing like 5 or 10% better under various conditions, from completely oncoming flow to yawed flow. And interestingly, the swept blades are more immune to yawed flow compared to the straight blades. So that means that they're more robust for different conditions in real life. And finally, they found that the wake unfortunately takes longer to recover behind a swept blade rotor, in this swept blade rotor at least, but that does make sense because this swept blade rotor is taking out more energy of the flow than the straight blade rotor, so that's to be expected. And that's not necessarily a bad thing because it means you're getting more power. So that's in this podcast. If you liked it, make sure to like, subscribe, and if you want to get better at CFD and theory, for example, like this, check out our courses in the link in the description. And if you want to make your experiments better, then check out the Atmosphere Hawk. That's an instrument that we make to accurately measure the density of the air that you're using. And this is important because the density of air changes between 2 to 4% every day. That's just due to changes in pressure, barometric pressure, and humidity. And between seasons and weeks, that does change even more, up to 10 or 15%. So if you are not measuring the density of air, it means that the velocity of your wind tunnel is not what you think it is. The forces that you are getting are not what you think it is. I think they are. The non-dimensional coefficients that you calculate are not the same as what they really should be. There are all these errors. And in terms of CFD validation, if you all these erroneous measurements make CFD much harder, because when you're trying to validate your model, you're using different densities, and you're going to get different forces. You're going to get different velocities, different wake profiles, everything, different vortex breakdowns, different von Karman Street formations, everything. So the Atmosphere Hawk gets rid of that error for you and makes your experiments and CFD much more reliable and easy. So check that out and then link in the description. And I'll see you in the next podcast. Peace out, amigos.